Good day, I'm Norman Wildberger. Today we're going to shift towards propositional logic and try to move towards understanding that in a very novel and powerful way using the algebra of Boole that we're now quite familiar with. So it will turn out that there are a lot of parallels between the propositional logic story and the electrical engineering story of circuit analysis. But there are also some interesting differences that I think are important also for the electrical engineering story. So historically, propositional logic is actually a branch of philosophy, not mathematics, but rather philosophy. And it has its origins in the attempts to systematize certain kinds of reasoning. Historically, the origins go back, of course, to Aristotle and to the Stoic philosophers in ancient Greece, in particular to Chrysippus. And it's actually perhaps the Stoic philosophers that are more in the direction of the kinds of setting up of logic that propositional logic deals with. Here's an example of the kind of statement that the Stoic philosophers were interested in making. If the first, then the second, but the first, therefore the second. So what does this mean? So it's referring to two propositions referred to as the first and the second, and the point is that we don't really need to concern ourselves with the exact nature of those propositions. We'll just call them the first and the second. So this first line here is telling us that there's a relationship between the first proposition and the second proposition, that if the first proposition is true, then the second proposition is true. So that's one thing that we know. And then the statement, but the first. That means that in addition, we know that the first proposition is true. This but can sort of be interpreted as an and. And then the conclusion is, therefore, the second. So if P implies Q and P holds, then we can deduce Q, usually called modus ponens. And here it is in a kind of a formulaic approach. P implies Q and P, those two things together imply Q. So now here we're introducing this symbol, sort of an upside down V, for and, that's usual thing in logic, and we have this symbol here, the implies operation. Okay, so today what we want to do is we want to give you an overview, an introduction to some aspects of propositional logic, with ultimately the aim of replacing a lot of that with the much simplified algebra of Boole approach. So it's not important for us to get an extensive treatment or familiarity with propositional logic because we're going to be replacing most of the key technologies with our new technology shortly. Here is an example of a classical logic puzzle in propositional logic. And it's due to Lewis Carroll, who wrote Alice in Wonderland and wrote a book or two on logic puzzles for people. Okay, so it's in the form of a certain number of statements which you are supposed to accept. And then there's a conclusion which you want to find. So here are the statements that we want to accept. No interesting poems are unpopular. No modern poetry is free from affectation. All your poems are on soap bubbles. No affected poetry is popular. No ancient poem is on soap bubbles. Now, this kind of statement, of course, involves English language. And part of the trick is that some of the statements here are kind of disguised so that it's not directly obvious what the direct meaning is. So that's part of the trick here. But of course, there's all these English words that are being used here, and so there's some subtleties as to what they actually mean and so on. But the idea is that even if we are not entirely clear about, what a poem is or what an affectation is or, what a soap bubble is or something, we can still sort of look at the bare bones skeletal logical structure of these statements and try to deduce something. And as a fun little exercise, you might like to figure out what is the conclusion of all this. I'll give you a hint. It has something to do with your poetry. Okay, so the meaning of the phrases or propositions which are involved here is in some sense not really relevant. The important thing is the relationship between these propositions and their truth values, where we kind of have this idea that there's true and false out there, and that propositions can be true or they can be false. Now, this is really more of a philosophical setup, okay? It's not really true and false in a mathematical orientation. It's philosophy and maybe, common use of language which we're investigating here. So propositional logic concerns itself with sort of atomic propositions, very simple statements or sentences, which are then combined to create longer sentences or propositions or sometimes formulas by the use of certain connectives. So for example, we might have our basic propositions be, say, capital P, capital Q, and so on. And then we're going to consider some fundamental relations between them. And these are the fundamental ones. And or not implies an equivalent. So P and Q. If P is a proposition and Q is a proposition, then P and Q is another proposition. It's like a compound proposition created from these atomic ingredients. Or this one, P or Q. Or not P. Or P implies Q. Or P is equivalent to Q. So these are the kinds of connectives that we use in propositional logic to create bigger compound propositions from the basic atomic ones. So if we go back to Carroll's puzzle, then you can sort of identify the basic ingredients are these little propositions, and we can give them names with capital letters. So I could stand for it is interesting. M stands for it is modern. Y stands for it is your poem. P is it is popular. A stands for it is affected. S is it is on soap bubbles. And then you can check that the various statements that we wrote down for Carroll's puzzle amount to, ultimately, the statements that I implies P. If it's interesting, then it is popular. M implies A. If it is modern, then it is affected. That means it's not free from affectation. And so on. If it's your own poem, then it is on soap bubbles. And here's some knots. If it is affected, then it is not popular or unpopular. And not M implies not S. If it is not modern, that is ancient, then it is not on soap bubbles. So this is a way of encoding efficiently, almost mathematically, the various compound statements that are built up from these atomic ones that are the ingredients, the starting points for the puzzle. And the idea is to find an interesting conclusion for it. So now we're obliged to say what exactly we mean by those various connectives like and or, and implies, and so on. And that's in terms of truth values of propositions. So we suppose that our atomic propositions are well defined and meaningful, and moreover that they can be assigned the value of true or false. This proposition is true. This one is false. Okay? So that's important. And ultimately, there's a lot of philosophical conundrums associated with this. I mean, we're not making an investigation about what is true and false. Philosophers can debate that for years and years. We're just assuming that you have a notion of true and false, and that we're able to assign these labels to our various propositions. So that's a kind of assumption that we're making. So true is represented by a capital T here for us, and false is represented by a capital F. And then here are the definitions of these various connectives in terms of the values of P and Q. And this will be very familiar to the algebra of Boole kind of story. So the various possibilities for P and Q are either false or true. So we can have them both false. P could be false and Q could be true. P could be true and Q could be false, or they could both be true. And then we define P and Q. That is the compound proposition whose truth values will be as recorded here. If both of these are false, then the and is false. If one of them is false and the other is true, then it's still false. It's only true when both of the ingredients are true. So that's and. Here is or, which you will recognize as an inclusive or. So it's true when one or both of the inputs are true. It's only false when both inputs, both ingredient atomic propositions, are false. Not P is just the negation. So if P is false, then not P is true. If P is true, then not P is false. And here's the implication relation. P implies Q. Going back to the Stoics, and arguably questionable as to whether this is a valid capturing of what people usually mean when they say P implies Q. But anyway, this is the definition that we're going to assume for this relation. So if P is false and Q is false, then P implies Q is true. So false implies false is true. False implies true is true. The only one that's not true is true implies false. It's not true that something that's true implies something that's false. That's the meaning of this F here. And true implies true. So if you like, you can just think that this is just a definition of what this symbol means, how we assign truth values to this combination in terms of the truth values of P and Q. And P equivalent to Q, well, that will be true when they're both false or when they're both true. And if they're not the same, well, then the equivalence is false. Okay, so this is obviously close to the Boolean algebra or algebra of Boole story that we've been talking about with circuits, but it is a little bit different. The setup is quite different, although we'll see that the mathematics of it is very parallel, which will be great for us because then we'll be able to apply the algebra of Boole ultimately to this story to revamp what's really going on here. Now, propositional logic starts off with these sort of atomic propositions, but then wants to build up compound or composite propositions by putting a lot of them together with these various connectives or logical relations. So here is an example. So here's a new proposition, which is not an atomic one. It's created from P, Q, and R, which are some basic propositions that have been established somewhere. So what is this big thing? Well, there's various brackets here. So there's a big bracket here. So all of this implies this. So what's in here? Well, it's an and between this thing and between this. So here we have P and Q implies R. That's a new proposition. And P implies Q. So the cumulative effect of taking this and this implies P implies R. Okay, so this then is a composite proposition. And we could ask, well, if we know the truth values of P, Q, and R, what are the possible truth values of S? So the standard way of doing that, at least when we start out, is to create a truth table. And it's very similar to the kinds of things we've been doing with circuits. Here are P, Q, and R, and here are the various 8 possible assignments of truths and false to those, starting with FFF and working our way down to TTT. And now I'm going to just write down the corresponding truth values to these sort of expressions that occur in here. So we can do this all at once with a little bit of practice. So let's have a look at P and Q implies R. Okay, so we're going to go through each one of these rows. So with this first row, P and Q, so F and F, false and false. If P is false and Q is false, then P and Q is also false. So the left-hand side here will be false. False implies false. Is that true or not? So we have to remember our implication. False implies false is true. So the value of this composite here is true for these inputs. And in fact, you can check that they're all true except just this one here. With this row here, the left-hand side would be P and Q, so that'd be true. And the right-hand side would be false, so true implies false. That's the one situation where the implication is false. That explains that F there. Okay, these are simpler. This ingredient here, P implies Q, P implies Q. False implies false, true. False implies false, yes, true. False implies true, yes. False implies true, true. True implies false, false. True implies false, false. True implies true, true. True implies true, true. And same with P implies R. Now we're looking at these two. False implies false. Whenever we have a starting of false, it'll be automatically true. And true implies false, that's false. True implies true, true. True implies false, false. And true implies true, true. Okay, great. So now we are in a position to evaluate S. Okay, so let's do that. So what is S? S is this cumulative thing. So that's obtained by taking this thing and this and asking, does that imply this? Okay, so let's do that. So true and true. That's true. Does true imply true? Yes, it does. Or in other words, that's true. This and this, well, it's the same. These are all the same, so they're all true. Okay, well, how about the next one? True and false. Well, that's false. Does false imply false? Right, because we have to take the and of these two and ask, does that imply this one? So the and of these ones is false. Does false imply false? True. The next one, true and false, is false. Does false imply true? True. Again, another false. Does false imply false? That's true. Does true imply true? That's true. So we see something a little bit interesting about this particular S. This is a compound proposition that turns out to be always true, no matter what the various truth values of the ingredients are. This is a special situation. It's always true, so this is some kind of like a theorem in the propositional logic world, although it's not called a theorem. So a few definitions. We'll say that a composite proposition, sometimes called a propositional formula, S, is a tautology if it is always true. So that example that we just did shows that that particular S was a tautology. It's always true independent of the truth values of the ingredient propositions. We'll say that it is a contradiction if it is always false. We'll say that it is satisfiable if it is sometimes true. If there's at least one input values for which we get a true. Now these are the standard definitions, but for me, I need to have closure, so I need to also have a definition of the other case. What do we call something if it is sometimes false? So there should be a name for that, and so I'm proposing that we call such a proposition debatable. Okay? Something is debatable if it's not true all the time. It may be true often, most of the time, but if it's not true all of the time, it's at least one time where it's false, then we'll say that it's debatable. Now maybe you know some other terminology for this, you can let me know, but in any case, we could perhaps use that. Okay, so these are special kinds of definitions that sort of allow us to identify things. Tautologies are especially important because they are like theorems. They are sort of special things which are some sense true. Okay, so that's kind of important. But the satisfiability story is also important because that naturally connects to satisfiability for logic circuits. Now, creating a truth table, as we've done, is a surefire way of analyzing propositional formulas to find out, where they fit into this hierarchy. But it is cumbersome because if the number of ingredient propositions gets large, let's say we have 10 propositions, then we're going to need 2 to the 10 rows to go through all the possible values of falses and trues that we can assign to these 10 things. So that exponential increase in the number of rows that you have is a serious obstacle to dealing with bigger expressions with lots of propositions. But nevertheless, this is a tried and true method that all students have to start with. So we start by making truth tables so that we understand the meanings of these various logical relations and how they work out. Now, what about when we have 2 formulas, say S and T? Well, an important notion there is that they are equivalent precisely when they have the same truth values all the time. So no matter what the input truth values are, the 2 formulas S and T always have the same outputs or the same values. Another way of saying that is to use the equivalence relation. So I remind you, S is equivalent to T precisely when the outputs are the same. Okay? F is equivalent to F, T is equivalent to T, but F is not equivalent to T. So another way of stating this equivalence is to state it in terms of this bigger compound proposition, S equivalent to T, that should always be true. Always being true is that it's a tautology. And in propositional logic, it's important to understand some basic tautologies that appear all the time, because they are important to be able to replace certain expressions with other expressions, typically simpler ones. So here are some examples of important such equivalences that allow us to simplify things. So here's S. It's some proposition. And here is F. That refers to the proposition which is always false. So it's the column of F's. Okay? So if we have S and F, well, that's equivalent to F. And conversely, S or F is equivalent to S, and S or T is equivalent to T. S and S is equivalent to S, and S or S is equivalent to S. Now I have to say just a little bit about the relative order in which we're thinking about these operations. You can see here, I hope, that this AND operator is a tighter operator than this equivalence. So this is interpreted as having a bracket here. Okay, and same with all of them. Okay. But we don't want to have too many brackets if we can avoid it, so we make the assumption that if we don't have brackets, then an expression like this, the AND sort of goes first, and then the equivalence. Okay, so here we have S and S is equivalent to S. Here, S or S is equivalent to S. And here, commutativity, S and S is equivalent to T and S. S or T is equivalent to T or S. And here is associativity. S and T and R is equivalent to S and T and R. Or S or T or R is equivalent to S or T or R. So these are sort of basic logical relations or equivalences that allow you to manipulate expressions, because if this kind of thing appears, then we're able to replace it with this because they have exactly the same truth values. That's what this equivalence means. Right? So all of these are important tools in propositional logic, in classical propositional logic, to simplify big expressions, which is one of the aims that one has. All right, so the equivalences are important for the simplification reason, and here are some more important equivalences which are a little bit more sophisticated than the other ones I've shown you. And if you're taking a propositional logic course, you have to get all of these under your belt. Okay, so here we have what we call the distributive law. We've seen this already in the context of circuit analysis, where we distribute. So R or S and T is equivalent to R or S and R or T. And the same thing with the ors and ands replaced. R and S or T is equivalent to R and S or R and T. Here are De Morgan's kind of laws. R and S is equivalent to not R or not S. And I'm putting the brackets here, so this is how we interpret it. We also have this assumption that if we have something like this without brackets, it really means this. Okay, so this next line is R or S is equivalent to not R and not S. This one's quite important. It gives an alternate description of the implication in terms of an or. So R implies S is equivalent to not R or S. This one's simple, just a double negation. Not R is equivalent to R. And this one here is basically the negation of this. Not R implies S is equivalent to R and not S. So all of these would be well studied and memorized if you were taking a propositional logic course, and they would be kind of ingredients that you would use to simplify complicated expressions. And it really is the same technology that electrical engineers use when they're simplifying Boolean expressions. Really exactly the same kind of technology. Even though really this came first, right? This propositional logic was more in the direction of what Boole was really doing when he was trying to apply mathematics to logic. He was really trying to bring out the mathematical side of things. But philosophers before that had been interested in that, going even back to the Stoics, of trying to find rules that allow us to sort of systematically, even mechanically, simplify expressions like this for the purpose of streamlining reasoning. So to be honest with you, I think it's fair to say that this direction of propositional logic, even though it may appear powerful and enticing from an external point of view, it actually is ultimately quite ineffective in dealing with the kinds of issues that is really directed towards, namely systematizing reasoning and argument out in the real world. And one of the reasons is that this entire framework does not address the underlying meanings of the propositions. And it doesn't address the critical issue of what do we mean by true and false. It's a dramatic simplification to think that, statements in real life are either true or false. Typically, you only get either true or false in mathematics. It's almost a characterization of mathematics. Any other discipline, there's always some grayness. It's sometimes true and sometimes false, maybe a little bit more true, depending on who you talk to and what day of the week it is, etc. Okay? And then the issue of what the underlying words mean. Any modern discussion about social policy or politics or religion or whatever has all these underlying words that are being used whose meanings are crucial to the argument. And so if you're not going to address the meanings of the words in the arguments, then you're never really going to be able to get at really important arguments. Okay? So if you're not a philosopher, I do want you to be aware that this entire direction, okay, is of very limited value for actually solving real life conundrums in terms of arguments and reasoning processes. In fact, I think this propositional logic really rose to the surface when it was discovered that the underlying mathematics was really parallel to that in the electronic circuit story. That is what really gave it the interest. Okay? The fact that all of this technology could be almost verbatim applied to analyzing digital circuits. That is sort of the killer application of all this, not actually to reasoning. Even though it can shed some light on individual problems and puzzles, and in the course I will give you some examples of that, but they're all rather specialized and not of great general utility. Okay, but nevertheless, it's still an interesting kind of discussion. So, to summarize, the main techniques for establishing or simplifying formulas in propositional logic fall roughly into three categories. There are the truth tables and just systematically writing down all the possibilities. Then there are using equivalences or substitutions based on these Boolean algebra identities really that we've just been talking about. These equivalences are like Boolean algebra identities, and they allow us to transform complicated formulas hopefully into simpler ones that are more manageable. Now there's another technique which uses inference rules, which I'm going to also be talking about. Okay, so there's going to be three quite independent approaches or techniques that philosophers have developed to simplify or to reduce complicated expressions to simpler things, to be able to ultimately come up with valid reasonings, valid deductions. But all of these techniques are going to be subsumed by the algebra of Boole. Okay? That is the main story here, that ultimately all of these three are vulnerable. Okay? And each of them can be replaced just by an algebra of Boole orientation. So I don't in fact want people to become adept at these things. I think we're going to subvert all of that and put in place a much more direct, simple thing. So basically, I think, courses in propositional logic, we're going to be really shaking the foundations of that discipline. Okay, so that's what we're aiming towards, but I do have to tell you more about these things here. So in our next video, I want to show how the algebra of Boole actually does allow us to basically avoid truth tables and this Boolean algebra identity dependence on equivalences and substitutions. Okay, so a very powerful new technology that will basically sweep aside all this established theory. I hope you'll join me for that. I'm Norman Wahlberger. Thanks for listening.